Today we're going to be looking at a task that asks us to explore quadrilaterals. We're going to create a quadrilateral and then place the midpoints on each side of our quadrilateral to inscribe a new quadrilateral inside the first one. We're then going to make some observations about the relationships between the interior and exterior quadrilateral, and further explore to prove one or more of the observations or conjectures we made. This task can meet, but is not limited to, the following high school geometry Common Core state standards and mathematical practices. We're going to prove the slope criteria for parallel lines. We're going to prove theorems about parallelograms and make formal geometric constructions using dynamic geometric software. Today we're going to be using the Geometer Sketchpad. This problem can attend to all 8 of the mathematical practice standards. We're going to get started by creating a quadrilateral labeled ABCD. We're then going to select the line segments on the outside and construct the midpoints. Those midpoints need to be labeled EFGH. And we're going to connect them to make our interior quadrilateral. Next, we're going to spend some time dragging our points around and observing how our quadrilaterals change. The first question that I was interested in asking was, what is the relationship between these 4 outside triangles and the interior quadrilateral? The way that I chose to answer those was by taking some measurements and seeing how they compared. I'm going to use the measurement tool to measure all of the areas, each 4 triangles, and the area of the interior quadrilateral EFGH. I'm noticing that the area of all 4 of the triangles is smaller than the area of the quadrilateral. And when I decrease the area of the triangles, the area of the quadrilateral decreases. This made me wonder if maybe they are equal to each other. We can use this calculation to show that the area of quadrilateral EFGH is equal to the sum of the 4 triangles created by the interior quadrilateral. I also thought, since these 2 areas are equal to each other, they must be equal to 1/2 the total area. So we're going to measure the area of the whole quadrilateral and then calculate half of it to discover that the area of an interior quadrilateral created by the midpoints of a larger quadrilateral is half the area of the larger quadrilateral. This is true no matter what direction you drag your points in. We can also prove this using reflections. You can see that the area of the reflected triangles fills the quadrilateral. so we can dynamically prove that these areas are equal to each other. I'm now going to hide these reflected triangles. And I'm also going to hide the triangles on the outside so that we are once again just looking at quadrilateral ABCD and quadrilateral EFGH. While I was dragging, I noticed that these line segments appear to be staying the same length. So I'm going to measure the line segments of the interior triangle. Right now, they're all the same length. But when I drag two of these points, you can see that the ones opposite each other stay congruent all the time. Specifically, line segment EH and line segment FG, as well as line segment EF and line segment GH. This got me asking questions about the angles of this quadrilateral. So I'm going to measure the interior angles as well. I can select all four at the same time and show that I have two sets of congruent alternate interior angles. So the alternate sides of the interior quadrilateral and the alternate interior angles of the interior quadrilateral are congruent. Since both of these observations are showing properties of the parallelogram, I decided to check for parallel lines. I'm going to create a parallel line parallel to line segment EF and going through FG. I'll know it's parallel if it also goes through point G. And therefore, we can prove that FG is a line segment on a line parallel to EH, making line segment EH and line segment FG parallel to each other. Since the definition of a parallelogram is to have two sets of parallel lines, we will check this by constructing a parallel line parallel to line segment GH. Since line segment FE does fall on that parallel line, we can confirm that an interior quadrilateral created using the midpoints of a larger quadrilateral is a parallelogram. If it's a parallelogram, the opposite line segments will have the same slope. So we can measure the slopes to prove that these line segments are in fact parallel to each other. In a parallelogram, the diagonals will bisect each other. So these line segments should be equal to each other, and they are when we measure. And that means that these line segments, HI and IF, will also be equal to each other. Let's make sure we get HI, and they are equal as well. To conclude, an interior quadrilateral created using the midpoints of a larger quadrilateral is a parallelogram.